Hello everyone and welcome to this research seminar talk by me. My name is Ráth, and today I'm going to talk about one of my favorite research topics, which was my PhD topic back in the day, but I keep working on it up to this day. So I will talk about Erdős-Rényi random graphs and forest fires and how they generate self-organized criticality. Don't be scared. So if you do not know any of these words, these will all be introduced and explained in the talk. And I hope that this little introductory talk will help you get a glimpse into the phenomena of self-organized criticality as well as the mathematical methods that we are using to tackle it. So here's a quick outline. First, I'm going to introduce the forest fire model, the model that I will study. And then, before I move on explaining its self-organized critical behavior, first I will have to take a step back and I will only study the case without fires, which is called the Erdős-Rényi random graph model or the dynamical Erdős-Rényi model. So this is a classical random graph model. But I'm going to take a look at it using an unusual lens because I'm going to explain how the giant component emerges using differential equations called the Smoluchowski coagulation equations. Then, after introducing this notation, I will be able to talk about our main result, the self-organized criticality of the forest fire model, and how an associated modified version of this system of differential equations called the controlled Smoluchowski equations. So this is the outline. So let me begin with the definition of the forest fire model. So we are going to talk about G and T, which is a graph on n vertices at time t. So this is going to be a random graph which evolves in continuous time. It's going to be a continuous time graph valued Markov chain. And the graph is going to have n vertices, and it's only the edge set that's going to change over time. And imagine that n is a very big number. So here is a bit of notation. So at time t, an edge of the graph can be either occupied or vacant. So occupied means that the edge is there, and vacant means that the edge is not there. And all of the possible n choose 2 edges can be or not be there. This is the so-called configuration space of our Markov chain, or the state space of our Markov chain. And we are going to investigate the asymptotic behavior of the component sizes in this graph as n goes to infinity. So that's going to be the object of our study. Every graph can be decomposed into, can be partitioned into connected components, and we will study how the sizes of these connected components evolve in time when n is very large. In fact, we will have asymptotic results as n goes to infinity. So first, let me try to define this Markov chain, the dynamics. It's kind of easy to explain. On the one hand, vacant edges become occupied with rate 1 over n. What does that mean? So if there is an edge which is vacant, so if the edge is not there, then imagine there is an exponential clock with rate 1 over n sitting on that edge, and when that clock rings, we just turn that edge on. Keep in mind that 1 over n is a very small number, so the rate of this clock is very small, so the expected time when such a clock rings is equal to n, and n is a big number. So vacant edges become occupied with rate 1 over n, and if this was the definition, then this would be the dynamical definition of the Erdős-Rényi random graph. Every possible edge turns on independently from the others with rate 1 over n. However, and this makes your graph grow. This is how the forest grows. So these edges keep on appearing, and the graph gets bigger and bigger. But any fixed time t, what you see is called an Erdős-Rényi graph. However, our dynamics is going to be a bit more complicated because on the top of creation there is destruction. Namely, each vertex of my graph is exposed to a Poisson point process of lightnings, and the rate of this lightning at one particular vertex is going to be denoted by lambda n. So the rate of lightnings depends on n, and I will specify the rate of lightnings later. So now I just denote it by lambda n. And if a lightning strikes one of the vertices, then it immediately, the fire spreads along the occupied edges at that particular instant of time and burns them immediately. But the number of vertices remains unchanged. So imagine that these edges are made of inflammable material, and once a lightning strikes one of the vertices, the fire immediately spreads through these inflammable edges and burns them. So that's it. This is the dynamics of the forest fire model. There is creation, there is destruction, and it leads to very interesting behavior. So let me start immediately by telling you the main phenomena that we want to investigate today, and it is called self-organized criticality. So the reason why we define this model is that this is a nice model of self-organized criticality, and this is going to happen when the lightning rate per vertex is much bigger than 1 over n but much smaller than 1. So if the lightning rate per one vertex is very small, so lambda n is much smaller than 1, but the total lightning rate received by the whole graph is much bigger than 1. So if the lightning rate per vertex is much bigger than 1 over n, then you multiply this by n because you have n vertices, then suddenly the total lightning rate received by the whole graph is n times lambda n, and if that's very big, then what this will cause is that this dynamics will not allow giant connected components to grow. These giant components will burn down immediately. However, small connected components will not feel the lightning. They are safe from these catastrophes. So somehow this asymptotic of lightning rates will only kill big connected components. And this way, somehow, the moral of the story is that the small rate of lightnings eliminate the big connected components, and the philosophy is that the forest fire is the mechanism that protects the forest from becoming very inflammable. So if there is a huge connected component of trees in your forest, then it's very dangerous and it's going to burn down very quickly, and that's a big catastrophe. But if there is a constant rate of lightning hitting all over the place, which is big enough to kill huge components, but it's so small that it leaves small components alone, then this dynamics will keep the forest on the verge of catastrophe, so it will never allow a giant component to grow, and hence the forest in a self-organized way keeps itself in a state which is on the borderline of safe and very dangerous. So we will make mathematical sense of these statements later. But first, let me show you a little simulation. So let us denote by V superscript n subscript k of t the total number of vertices of the graph which are contained in connected components of size k at time t. And of course, by size here, I mean the number of vertices contained in that connected component. So let's see, this is a notation that we will use for the rest of the talk, but first let me just see what happens in our simulation. So let's say my graph has 9 vertices, and initially I start without any edges. So I have 9 isolated points, which means that V1 is 9. So the total number of vertices contained in isolated components is 9, so V1 is 9, but V2 is 0, V3 is 0, and V4 is 0 and all of the other values are 0 because currently there are no vertices contained in connected components of size 2, there are no vertices contained in connected components of size 3, etc. But if I draw an edge, then suddenly there are now there are only 7 vertices contained in isolated so there are only 7 isolated vertices, and now suddenly V2 is equal to 2, meaning there are 2 vertices contained in connected components of size 2. If I draw another edge, then now there are 4 vertices contained in connected components of size 2, and there are 5 vertices contained in connected components of size 1. I can draw one more edge. Now there are 6 vertices contained in connected components of size 2, and there are 3 vertices contained in connected components of size 1. Now, if I draw an edge here, then suddenly there is one connected component of size 3, so V3 is equal to 3, and now V2 decreased, so now there are only 4 vertices in connected components of size 2, and there are 2 vertices which are isolated. I can draw one more edge, and now I created a connected component of size 4, so now there are 4 vertices in connected components of size 4. But now something happens. This vertex turned red, meaning that now a lightning struck this vertex, and what happens is immediately the fire, denoted by red here, the fire spreads along the connections, the edges, and burns them. So now what happens is that this connected component of size 4 disappeared, so now V4 is 0, but V1, the number of isolated vertices, immediately increased to 6. But life doesn't stop here. Now I can keep on adding more and more edges and so on. Before I move on explaining to the self-organized criticality in a mathematically rigorous way, I first have to take a step back, and I would like to talk about a classical case, namely when lambda n is identically 0, so if there are no lightnings whatsoever, then my model is just the dynamical and Erdős-Rényi random graph model. And this is a famous random graph model which has already been known since the 60s when it was defined by Hungarian mathematicians Paul Erdős and Alfred Rényi. And what happens is when n is very large, then if t is strictly less than 1, so I forgot to mention, I start from the empty graph. I start from n isolated vertices, just like in my simulation. And then, if n is super big, but t is strictly less than 1, then what we see is that the Erdős-Rényi graph is in a subcritical phase, meaning that the connected components are very small in the sense that the largest component is only of size of order log n. So this is what we call the subcritical phase of the Erdős-Rényi graph. If, on the other hand, something very strange happens as t crosses 1, because if t is strictly greater than 1, then this graph is already in the supercritical phase, in the sense that suddenly out of nowhere a giant component appears, namely the size of the biggest connected component is already n times theta t plus some random fluctuation which is much smaller than n, where theta t is a positive number. So if t is strictly greater than 1 and n is very huge, then already there is some theta of t which is positive, such that the biggest connected component is of size n times theta of t. So the largest component already contains a positive fraction of the vertices. However, there is one giant component and all of the other connected components are very small. They are like in the subcritical graph, the second largest component is only of size of order log n. And I forgot to mention, or I did not mention, the strangest thing that you can only observe at t equals 1. So for a split second, something strange happens as the graph morphs from its subcritical state to its supercritical state. At t equals 1, the graph is in so-called critical state. And in here, the size of the largest connected component is of order n to the 2/3, and the second largest connected component is also of order n to the 2/3. So this is a very strange state that is different from both the subcritical state, because the largest component is much bigger than log n, but it's also different from the supercritical state when the largest component is of size n. So n to the 2/3 is much bigger than log n, but it's much smaller than n if n is very large. So this is the phase transition of the Erdős-Rényi random graph. This is well known, but in this talk we will not focus on the size of the largest connected components in the forest fire model or in the Erdős-Rényi graph. We will focus on the sizes of small connected components, and that is going to help us understanding the self-organized criticality. As a matter of fact, the phase transition of the Erdős-Rényi random graph, it can be treated in a different way. You can also already see the phase transition if you focus on small connected components. Let me try to explain. So returning to my earlier notation, we denote by V superscript and subscript kt the total number of vertices in the graph which are contained in connected components of size k at time t. One thing to observe is that these component sizes themselves form a Markov chain, meaning if you do not see the graph, if you only see the sizes of these blobs, the connected components, so if you know the sizes, know this partition, but you don't know the exact graph structure inside the connected components, this is still enough to determine what happens next, how these connected components, how these blobs are going to merge. So this is itself a Markov chain. You don't have to know the past of these, the evolution of the blobs. It's enough to know the present state to be able to determine how it evolves. Let me introduce one further notation. So let me define by V superscript and subscript kt the 1 over n times V and kt. So this small v and kt is the total mass of vertices contained in connected components of size k at time t when I normalize the mass so that the total mass is equal to 1. So if I sum for all k, if I look at the total mass, so if I sum the masses connected in contained in components of size k for all possible values of k, then I get that the total mass is 1, because the total number of vertices in my graph is equal to n. So if I divide by n, then I get this. So or v and kt is the fraction of vertices contained in connected components of size k at time t. Now, here is the deal. There is a weak law of large numbers for the Erdős-Rényi model without forest fires as n goes to infinity. Here is how it is formulated. As n goes to infinity, for every fixed k and t, but n goes to infinity, this sequence of random variables vk and t, these fractions, they converge in probability to a deterministic value vk of t. So this is like the asymptotical value of the fraction of vertices contained in connected components at time t. For example, here is a very special case that's easy to understand without too much calculations. Let's look at isolated vertices. I claim that as n goes to infinity, the fraction of isolated vertices converges to e to the minus t. So Vn1 of t is the fraction of fraction of vertices contained in connected components of size 1, otherwise known as isolated vertices. So here is a heuristic proof of this. Let me start with V1 of t. First, I immediately start with the heuristic step, so that's why this Wiggle equality sign is here. So I claim that the weak law of large numbers holds, so this quantity is very close to its expected value. It's essentially, well, not II, so it's not the sum of IID summons, but something very close to that. Now, by the linearity of expectation, this expected value is equal to 1 over n. Well, the 1 over n is there because this is the normalizing factor in front of v1 of t, so this is 1 over n, and here I just have to sum for each vertex of the graph first inside the expectation I sum the indicator of the event that my particular vertex v has 0 neighbors. So dv is the number of neighbors, so the degree of v, and if the degree of my vertex is 0, that means he is isolated. Now I can take the expectation inside the sum by the linearity of expectation, and the expected value of the indicator of the event that my vertex has 0 degree is equal to the probability that it has 0 degree, and of course this value is the same for every vertex, and since my sum here contains n terms and I divide by 1 over n, this simplifies to the probability that any particular vertex, your favorite vertex, has 0 degree. But then, remember, at time t, each of the edges going out of vertex v is present with probability e to the minus 1 over n times t. Remember, edges turn on at an exponential, so the edge becomes occupied at an exponential time, and that exponential random variable has parameter 1 over n, so the probability that the clock does not ring up to time t, that's e to the minus 1 over n times t. But this was one particular edge going out of my vertex v, and there are altogether n minus 1 edges, possible edges, going out of my vertex v, so the probability that all of them stay closed up to time t, since they are independent, this is the same number raised to the power n minus 1. And then, since n is very big, this is roughly the same as e to the minus t. So this was This was a short heuristic calculation indicating that indeed what I stated, this law of large numbers, holds when k is equal to 1. And in fact, similar arguments, but albeit a bit more complicated, show that there is an explicit formula, and the vkt, so the asymptotic fraction of vertices contained in connected components of size k at time t when n goes to infinity, there is an explicit formula here, and this is okay. So this can be formula can be understood in various ways. But for example, this k to the power k minus 1, in one of the possible proofs of this formula, this k to the power k minus 1 comes from the so-called Cayley formula for the number of spanning trees on n labeled vertices. But I will not discuss the proof of this explicit formula, but I will give a different way of deriving this formula, Vk of t, which uses differential equations. But before I move on to explaining differential equations, I'll tell you how the phase transition of the Erdős-Rényi model, how can it be seen by looking at these deterministic values v1t, v2t, and so on. This is very funny because if you remember, the phase transition says that something very drastic happens at t equals 1. Somehow the behavior of the graph is very different when t is less than 1, and it's very different when t is greater than 1. And this is very strange. This is very puzzling because if you look at these formulas, they are continuous in t. So if you look at this formula, it doesn't really look that different when t is less than 1 and t is greater than 1. So all of these functions as a function of t are smooth, but still let me argue that this drastic change, the phase transition of the Erdős-Rényi model, this can be seen by looking at these functions. Namely, if t is subcritical, then the sum of these fractions is equal to 1. And also, if t is fixed, then vk decays exponentially, or vk of t decays exponentially in k. By the way, the fact that this sum is equal to 1, a priori, this doesn't look very surprising, because if you remember, if n was finite, then this sum was equal to 1. If you remember, this was reflecting the fact that all of the mass is contained in connected components of some finite size, and if k goes from 1 to n, then you counted all of the vertices once, and by our normalization, here I calculated all possible vertices once. So if I sum up these things and normalize by n, then I get the total mass, which is equal to 1. So this is not surprising that you see the same thing when n goes to infinity. The total mass is contained somewhere, so this sum has to be equal to 1. But here's a little surprise. When t is strictly greater than 1, so in the supercritical phase, if you look at these numbers that are defined here, so if you look at these quantities for some value of t which is greater than 1, and if you sum k from 1 to k goes from 1 to infinity, then you see suddenly something very surprising, that the total mass suddenly it is strictly less than 1, and by the way, still here vk decays exponentially in k. The reason for this is that the mass that's gone missing, so somehow as n went to infinity, mass escaped to infinity. The missing mass is going to be contained in the giant component. But before we move on, let me also mention the critical case. So when t is equal to 1, then the sum of the total mass is still 1. So still there is no giant component at t equals 1. The total mass of finite components is still equal to 1, but as opposed to the subcritical and supercritical phases, now the vk's at t equals 1 do not decay exponentially in k, but it decays much more slowly. It decays polynomially. It decays like k to the power minus 3 over 2. So these are things that you could prove yourself using Stirling's formula if you evaluate this vk of t. So this is kind of easy exercise in Stirling's formula, and I'm not going to do that. But there is one more thing that I would like to mention, that this mass missing, so somehow this sum is already strictly less than 1, but what happens that in the supercritical case, the size of the giant connected component in the Erdős-Rényi graph, if you divide it by n, the size of the giant connected component converges to this theta t, where theta t is exactly the difference of 1 and the total mass, which is strictly less than 1. So this is kind of hard to understand at first sight, but what happens here is that the giant component is so big that its mass is not registered for k equals 1. It's because the giant component is much bigger, or k equals 100. So here vk of t is the asymptotical fraction of vertices contained in connected components of size 100. But if n is 10 zillion, then the giant component is much bigger than 100. So the size of the giant component is not registered in vk of t, where k is, let's say, 100. So somehow there is a strange thing that there is a limit and there is a sum, and if you exchange the order of summation and limit, then you get different results. So this phenomenon is called like mass escapes to infinity. But the mass is there for all finite n, but it's in a very large connected component of order n. So this is all nice, but now I would like to point out a way to prove this phenomenon here that I list on this page. I'll show you a different way of understanding this deterministic phase transition that avoids using Stirling formula. So there is a more qualitative way of seeing this behavior, the subcritical phase, the supercritical phase, and the critical phase. There is a way to understand this without understanding this explicit formula. So this is kind of magical that in the Erdős-Rényi graph you have such an explicit formula, and there are going to be analogous quantities in the forest fire model, but those are not going to be explicit. So we have to develop a theory which gives these results, these conclusions, without explicit formulas. And that theory is going to involve differential equations. So what we are going to prove, or like I'm going to give a sketch proof. Still, we are in the Erdős-Rényi graph, by the way. So I'm going to explain to you that in the Erdős-Rényi graph, without forest fires, these quantities, these vk of t's, these asymptotic fraction of number of vertices contained in connected components of size k, these satisfy this differential equation. So of course the variable with respect to which we differentiate is t, but here I did not write out. Of course here I'm talking about the time derivative, that's why the dot is there. The time derivative of vk of t, and that's equal to minus k times vk of t plus this thing. And of course here also I suppressed the t from the notation. So I'm going to explain to you why this differential equation holds. So, and by the way, I forgot to mention this system of differential equations. This is called Smoluchowski's coagulation equations. And the fun fact is that this differential equation existed 100 years ago, while the Erdős-Rényi graph was only invented 50 years ago, maybe 50, something like that, maybe 50 or 60 years ago. So actually the system of differential equations describing the behavior of the Erdős-Rényi graph happens to be much older than the random graph itself. So this is a fun fact. So let me deduce this system of differential equations using martingales. But actually the argument can be understood even if you don't know too much about martingales. So don't be scared. So in the Erdős-Rényi Markov chain, meaning now if we only focus on the time evolution of the sizes of the connected components, then what you see, and so if you only look at these blobs, then if you have a connected component of size k and if you have a connected component of size n, they can merge if at one point an edge appears, a vertex which is in the left connected component and the right connected component. As soon as an edge appears, these two blobs are going to merge. And what I claim is that these blobs merge with rate 1 over n times k times L. So you have to multiply the sizes of the connected components and divide by n, and then that is the rate at which they merge. And of course, if they merge, then they are going to form, the merged component is going to be of size k plus L. So this is easy because k times L is the number of possible edges between these two connected components. One of them has k vertices, the other one has L vertices, so there are altogether k times L possible edges between them. Each of those vertices appears at a rate 1 over n. So the total rate at which an edge appears between these two connected components is 1 over n, the rate of an individual edge multiplied with k times L. That's it. That's just the property of exponential random variables. But then, if I denote by W superscript n k L t the number of such coagulations from 0 to t, so this is the number of coagulations that happen between connected components of size k and size n, then, oh sorry, that was just notation that I will need for my further calculation, and I also have to introduce another notation. C n k of t is just my previous quantity v n k t divided by k, so this is just not the number of connected components of size k. So if you remember, here what's in the numerator was the total number of vertices contained in connected components of size k, but of course each connected component has k vertices in it, so if you divide by k, I get the number of components of size k at time t. Now here's a little calculation. So if k is not equal to L, then I want to calculate the drift. So this L denotes infinitesimal generator operator acting on this quantity W, but let's just say that this is the drift of this quantity, or by definition this is just the limit as dt goes to 0, 1 over dt expected value of the increment of this quantity given the sigma, given the information available at time t. So this is notation that you might be familiar with from stochastic processes class or stochastic analysis class. So this is in some sense on average or expectation. So this is like a time derivative, but only in an expected value sense. So this is the drift of this quantity, and I claim that this drift can be expressed very simply. There are C and KT number of components of size K. There are C and LT number of components of size L. Each of those components, so if an edge appears between any of these components of size K and size L, then there is going to be an increase in this quantity. So, and that increase is going to be equal to 1. So I just have to, this is the total rate here. Okay, so let me back up. So this 1 over n times K times L, this is the rate that I mentioned up here. So if you multiply that with the CK and CL, then you get the total rate at which such a merger between a component of size K and a component of size L appears. And then, of course, by definition, if you multiply this quantity by K and if you multiply this quantity by L, then you get these other quantities. So now I get that this rate, the drift, is equal to Vk times Vl times 1 over n. And then if I rearrange it a little bit using my previous notation, then this is going to be equal to n times the asymptotic fraction, or sorry, no asymptoty yet, this is still for finite n. This is equal to n times the fraction of connected components contained in vertices, the number of vertices contained in connected components of size K, and the fraction of vertices contained in connected components of size L. So what we derived was that the drift of this quantity, the number of coagulations from 0 to t, this is an increasing number, so this number can only increase, and its drift is equal to this positive number. Now you can repeat this calculation, but now if K is equal to L, then the calculation is a little bit different because a component cannot coagulate with itself, so you're counting pairs. So now you this orange quantity here is a bit different than compared to the case when K was different than L, because simply this is easy combinatorics, since if you drop an edge inside the component, then it's not going to change the component size structure. Components only merge if different components, if you add an edge between different components. So that's why this quantity is here. And then kind of asymptotically forgetting about this -1 here, then heuristically this is going to be 1/2 times n times the square of V and KT. So compare this to the quantity on the previous page. There you had a product, but now you have a product of the thing with itself. If K is equal to L, then this is the square, but there is a 1/2 because of this thing that if a component of size K merges with a component of size K, then you only count it once and not twice. So recalling our previous notation, VWNKLT is the number of times when a component of size K coagulated with a component of size L before time t. Also, remember that V and K is the total weight of components of size K. So here is an equation that I can write down which connects these quantities. This is kind of similar to the differential forms that we had in stochastic analysis called stochastic differential. So on the left hand side you see the increment of the total weight of components of size K. So if you look at a tiny time interval and you ask yourself what is the increment of this quantity, the total weight, then it's easy to convince yourself that it can increase if two smaller components merge and form a connected component of size k. So this makes this quantity increase, but this quantity can also decrease if a connected component of size k merges with a connected component of any other size. So indeed, L goes from 1 to the lower integer part of k over 2. Okay, so this is kind of combinatorics. I already explained to you the idea, and I'm not going to dwell too much on this. The multiplier k is here because remember, this is counting the number of times when a component of size k coagulated with a component of size L, but of course, each merger is going to make a change of size k to the number of vertices, to the weight. Well, this weight is not normalized, but I'm going to normalize it in a second. Okay, so this is the stochastic differential, and then by taking the expected value of both sides of this equality, or more like there is an identity here, so I can look at the conditional expectation of both sides of this equality with respect to the sigma algebra ft, and then divide by dt. Then what we on the previous page we deduced the drift of these quantities that appear on the right hand side, and then this way we are going to obtain the drift of the left hand side. So if you take this sum and replace these stochastic difference, take the expectation, then you obtain that the drift of the left hand side is this thing divided by n. So the drift of the total fraction of connected components contained in the total fraction of vertices contained in connected components of size k, the drift of that is on the left hand side, and if you plug in this equation, the drifts that we have earlier calculated, then you obtain the right hand side, and you obtain that this is equal to this quantity. If you remember, there were these multipliers n, but since now I'm dividing by n because I'm not looking at the number but I'm looking at the fraction, then that capital N cancels out because I divide everything by n. So I get this very nice quantity which no longer contains explicit mentioning of n, only in the superscripts. And of course, there is a sum here, so there is also a sum here, but we will argue that this, or we know that this sum is equal to 1. This is just the total weight of connected components. So that is going to be equal to 1. And what I'm saying is that this already looks very similar to Smoluchowski's differential equation that we wanted to deduce. And indeed, so what we obtained, I'm just copying here the formula from the previous page, and here is the martingale bullshit. So you don't have to worry too much about this. This formula that I just derived can be combined with this other formula, which says that if you look at the increment of a quantity, if you subtract from it the integral of its drift, then it's well known that this is a martingale. Again, in stochastic analysis, if you remember, Ito processes had a drift term, and if you get rid of that, then the rest is called the martingale term. In any case, this is a martingale because you subtracted the drift, so this whole quantity has 0 drift, so therefore it's a martingale. And also, you can argue that this is a martingale which increases with small jumps. Therefore, using standard martingale technology, you can argue that its variance is very small. It's order 1 over n. So therefore, this martingale is actually, it's not very much random. So it's very much concentrated around its expected value. There are ways of making this rigorous. So since this quantity has zero, close to zero variance, so very small variance. Therefore, you can just simply argue that this integral equation holds, and you can pretend that the right hand side is zero. And of course, if an integral equation holds, this is my asymptotic integral equation when n is big. But if n goes to infinity, then actually if I let n go to infinity here, then I get my asymptotic value vk of t, and similarly on the right hand side. And then in the limit, you actually get an integral equation which holds exactly. And then if you differentiate that integral equation with respect to t, then you get the differential equation. But actually, heuristically, you have already seen. So if you looked at the drifts, you can already see the differential equation down here. So if you believe that these quantities are close to their expected values, and if you write down a differential equation of the expected values, namely the drifts, then you get this quantity, of course, also assuming that, or also keeping in mind that this sum is equal to 1. Of course, this sum is equal. You might say, hey, but what happens when the giant component appears? But you shouldn't worry too much about this, because these differential equations are about the small values of k. So a component cannot merge with itself, but since k is small and fixed, the total rate at which a component merges with someone else is effectively can be replaced by this quantity. So this was a long story. Now I managed to derive these differential equations, which are called Smoluchowski's coagulation equations. But sure, how to solve these? So on an earlier page, I magically mentioned an explicit formula, and these are exactly the solution. So there is a closed form for the solution of this system of differential equations. So one can check that this is a solution. But now I want to develop a method which says something about the solution of this system of differential equations without explicitly writing down the solution, because this method is going to be very handy when I finally move on to talking about the forest fire model. So I'm still only talking about Erdős-Rényi graphs. So here's the deal. Here is my sequence. So here is my system of differential equations. Actually, it's an infinite system of differential equations. For any, there is v1 of t, v2 of t, v3 of t, and there is this system of differential equations. But I say that instead of looking at an infinite system of differential equations, one can look at its Laplace transform, and then I claim that this new quantity is going to solve a partial differential equation. So I trade an infinite system of differential equations to PD. Namely, so I denote by Vt of x the generating or the Laplace transform of these quantities. So I look at, so x is a new artificial variable, and I take a convex combination, or well, so I take these functions e to the minus k times x weighted by these weights vkt, and I sum them up. And then of course this function, so you can retrieve so if you know this function, so if I manage to, so I will write down a differential equation for this new function, and I claim that if I solve this differential equation, and if I have an explicit solution for Vt of x, then I can retrieve these coefficients Vk of t from that. But I will not do that. But my point is that the Laplace transform contains all information about these coefficients. So I do not lose anything if I switch to Laplace transforms. And here's a quick remark. So since these quantities are positive, then the function that and this function, these individual functions e to the minus k times x as a function of x, these are decreasing, convex and analytic. Therefore this function vt of x is also going to be decreasing, convex and analytic. And for example, the density of the giant component, so the mass missing from the finite quantities, is just if you plug x equal to 0, then that is going to be that. So if you plug x equals to 0, then these quantities are all equal to 1, so you are just getting the total sum, and that was how we defined 1 minus theta t. So theta t was 1 minus this infinite sum, so vt of 0 is 1 minus theta t. And my point, and this is a calculation that I'm going to skip, that the time derivative of this quantity, if you differentiate term by term, so if you differentiate this, and if you switch differentiation and sum, then if you differentiate vk of t and plug in the right hand side, then that can be rewritten as the right hand side of this equality. The reason that if you differentiate this so if you differentiate this quantity with respect to x, then of course a multiplier by k pops out, and that's what you have here. And this thing, this sum, is actually a convolution. So the convolution, if you take the Laplace transform of a convolution, then it becomes a product. So that's why you have v squared, because you took the convolution of these quantities with themselves. But again, since there is a multiplier with k here, you also have to differentiate this thing with respect to x, and again a multiplier of k pops out if you differentiate these. So this is something that you can check, and this is a partial differential equation. But this is, at first sight, this looks a little bit scary, because, well, the good news is that this is a first order partial differential equation, so that's good news. But the bad news is that this is a nonlinear partial differential equation, because this v squared appears. But again, the good news is that this is a very well-known partial differential equation called the Burger's equation, and this is already a thing to celebrate. So we have already came on a very long journey. We started with the Erdős-Rényi graph, which is primarily understood as a combinatorial object. Then we converted it into analysis by looking at Smoluchowski equations, and then now we can take one more step and turn this whole question into a question of the analysis of partial differential equations. But the fun fact is that this equation can be solved explicitly, and this is what we are going to explain next. So there is a well-known way of solving one first order nonlinear PDEs, and that's called the method of characteristics, but it's equivalent to the following method. If you take this differential equation, oh, by the way, if I differentiate here, then of course I get this simpler form, so this multiplier 1/2 missing, so this is still the same PDE as before. And now a way to explicitly solve this is if I look at, this is a function, for each value of t, this is a function of x, but if I take the inverse function that I denote by vt of, denote by xt of v, the inverse function of vt of x in the second variable. So this is the definition of the inverse function. So if I plug in the xtv function into the vtx function for any fixed value of t, I get the identity. But then what I say, and by the way, I've learned that this transformation, so this is a classical way of solving nonlinear PDEs, and this is called the hodograph transform. So if you look it up, this method of solving any nonlinear first order differential equation, in particular the Burger's equation, this is called the hodograph transform. But if you use this transformation, then the PDE for the inverse function becomes super simple. This is so simple that it can be solved explicitly. So somehow the magic happened by taking the inverse function, and this differential equation is not even a differential equation. The right hand side does not depend on the unknown function. So you just integrate and you get that xtv is equal to x0v plus t times v minus 1. This couldn't be simpler, but what does this? So now this is fantastic. We solved the Burger's equation. Now let's see what conclusions can we draw regarding the phase transition of the Erdős-Rényi graph. So I claim that the phase transition, remember, here is on a couple of pages ago, here is, this was the phase transition. There was subcritical behavior, there was supercritical, and there was critical behavior, and I claim that all of this can be seen on the Laplace transform of these quantities. So let's take a look. If I start, so if you remember, this x0v, this was the inverse function of my initial function, but since initially I started from all isolated vertices, all of the mass was contained in components of size 1, then the Laplace transform of that is just e to the minus x, so the e to the minus x, so the inverse function of that is minus log of v. This is what we see here, and this is the plot of x0v. This is just the minus log function. But what's happening is that xtv is just the initial one plus t times v minus 1. So I'm starting to add here linear functions, and the slope of this function is t. So at time t, I take my initial function and I add to it a linear function which has slope t. So now the variable is v, and of course this little green blue line here intersects the horizontal axis at v equals 1. So this little function, linear function, has slope t. And of course, as t increases, this function that I add gets steeper and steeper. So what happens? If I add a function with a little slope, then now this is how my xtv is going to look like at a small time. And then something happens at t equals 1. So at t equals 1, this is how my function looks like. This is when xtv has 0 derivative here at this point. And of course, this right-hand side, this is red because only the left-hand side can be understood as the inverse function of something. So the black part is the inverse function of the Laplace transform, and the right-hand part is cannot be understood as that. So see, only the left-hand side is the inverse function of something. And then suddenly, if t is greater than 1, then the function that I add has so big slope then this part, so I can only understood the black part for which you can take the inverse function is suddenly looks like this, and the red part, the part that I have to ignore, is here. So what's happening here is that if t is not equal to 1, then the minimum of this function is negative. So if you look at any of these functions, the minimum is less than 0. Therefore, the inverse function can be extended analytically to a negative interval, which means that if the Laplace transform can be extended to negative values, that means that the coefficients of the Laplace transform decay exponentially, and this corresponds to this property that I mentioned here, that Vk decays exponentially in k for any value of t which is not equal to 1. And by the way, in the Erdős-Rényi graph, since the coefficients decay exponentially, heuristically that corresponds to the fact that the largest connected component which is not the giant, it has size of order log k. So if vk decays exponentially, then the largest value of k for which you see something significant is log k. But then, now I'm going to deduce the behavior that you see at t equals 1, namely you see this strange decay. So now these coefficients decay at a polynomial rate, and somehow heuristically this corresponds to the fact that at the critical time the largest connected component of the Erdős-Rényi graph is of size n to the 2/3. So somehow there is a magic, so there is a -3/2 here, which can be translated heuristically to n to the 2/3, the size of the giant, or the size of the biggest component, no giant at criticality. And now let me see how this thing can be seen on the Laplace transforms, and I will also explain why this theta t can be seen on the Laplace transforms. Now I kind of explain, I know some of you are already lost here, but I try to explain why vk decays exponentially when t is not equal to 1, and also the size of the giant component. If you remember, theta of t was equal to vt of 0. This is something that we said on this page, I think. So vt of 0 is 1 minus the density of the giant component. And already on this picture you can see that if t is less than 1, if t is less than 1, then this value, so maybe I'll look at the formula. So theta t is going to be vt of 0. So since that can be seen on the inverse function, so theta t is the point where xt of theta t is 0. And then if t is less than 1, then this intersection point is 1, but suddenly if t is greater than 1, then another intersection point appears, and that is going to be theta t. Okay, so probably now you're lost, but still I want to say one more thing. And at critical time, what you see is that the inverse function has derivative 0 at 1, which somehow corresponds to the fact that the Laplace transform near x equals 0 decays like square root of x, and then there is a way to relate the behavior of the Laplace transform near 0 to the decay of the coefficients, and then you can use the so-called Tauberian theory to deduce from the asymptotic behavior that you see on this picture. You can infer the asymptotic behavior, the polynomial decay of the coefficients. So that's okay. That was hard to swallow, but now finally I can move on and explain the self-organized criticality of the forest fire model. Hooray, hooray! So the technical part of this talk is over. So now let the fun part begin. So now we are equipped with the language to talk about self-organized criticality. If you remember, there was this lambda n, which was the rate of lightning per vertex in the model, and we assumed that this rate of lightning per vertex is much bigger than 1 over n, but much smaller than n as n goes to infinity. This is what we call the critical domain, or this is what we have to assume about the lightning rate, because since lambda n goes to 0 as n goes to 0, the fire does no harm to connected components of a fixed size, because if you have a connected component of size 5, then each of those 5 vertices are going to be hit by lightning with the rate lambda n, but since lambda n is very small, if n is big, then this component should not be afraid of lightnings. But if you have a big connected component, so if there is a giant component whose size is comparable to n, you know, in the original Erdős-Rényi graph that happens. So if you would have a giant component with size comparable to n, then all of the vertices inside that component receives a lightning with rate lambda n, and since we assumed that lambda n is greater than 1 over n, therefore n times lambda n goes to infinity, that means that giants would burn immediately. So this is what my fire is doing. It leaves small components alone, but it kills giant components immediately. And under these assumptions, here is the main theorem about forest fire models. This was proved in my PhD thesis. I claim that similarly to the Erdős-Rényi case, there are these deterministic functions vkt such that if you look at the fraction of components contained, if you look at the fraction of vertices contained in connected components of size k in the models in the model where you have n vertices and you let n go to infinity, then there is a weak law of large numbers for any fixed value of t, namely these quantities converge to an asymptotic deterministic value vk of t. So that's the theorem, that you also have weak law of large numbers in the forest fire model for any fixed value of k and fixed value of t as n goes to infinity. However, these deterministic functions that arise in the limit behave very strangely. Their behavior is quite different from what we have seen in the Erdős-Rényi graph. Or, well, to be more precise, if t is less than or equal than 1, then vk of t is the same as in the Erdős-Rényi Smoluchowski case. And this shouldn't be very surprising, because if t is less than or equal than 1, then remember, even in the original Erdős-Rényi graph without any lightning strikes, the connected components were small, and since our lightning rate is very small, the lightning leaves the small components alone. So when t is less than or equal than 1, then the lightnings does not do too much harm to the forest. On the other hand, and here is the deal, here is the punchline, when t is greater than equal to 1, then we see entirely different behavior. These quantities vk of t behave like this. Their sum, the total weight, is equal to 1, and for any value of t which is greater than equal to 1, the decay in the variable k is polynomial, and the exponent of that polynomial is the same minus 3 over 2 that we observed in the critical Erdős-Rényi graph. So this is something very strange. In the Erdős-Rényi graph, you've seen this very strange exotic behavior of polynomial decay of the vk's for only a second at t equals 1. You blink and you miss it. If t is smaller than 1, or if t is greater than 1, then these vk's decay exponentially. And in the Erdős-Rényi graph, it was only at t equals 1 when you have seen this, that the total mass is 1, so no giant component, and you've seen polynomial decay. As opposed to this, in the forest fire model, for any t greater than equal to 1, you can enjoy this very nice exotic behavior of polynomial decay. So for any t greater than equal to 1, you see a behavior which is qualitatively very similar to critical Erdős-Rényi random graphs. Of course, the coefficients change, they evolve over time, so these are not the same as in the t equals 1 case. They evolve in time, but their asymptotic behavior remains very similar to critical Erdős-Rényi. Hence, the name self-organized criticality. This model organized itself in a way that once it arrived at criticality, so it took some time to arrive at criticality, but once it did, and that happened at t equals 1, it somehow stays there. The system organizes itself in such a funny way that for any t greater than equal to 1, it stays critical. It cannot really go supercritical because because the fire would kill giant components immediately, but it cannot really go back to subcritical either because, well, that's harder to explain. So that is self-organized criticality as observed in the forest fire model. One further thing to celebrate is that these limiting functions Vk that we obtain in this theorem, these are they do not depend on the exact decay rate of these lambda n. So here I could choose lambda n to be 1 over square root of n, or I could choose it to be 1 over cube root of n. Both of these choices satisfy these asymptotic criteria. I would get asymptotically exactly the same functions. So somehow the lightning rate, as long as it's in this regime, the lightning rate does not really affect the asymptotic densities. So we did not really have to fine-tune the model to see this permanent criticality in the limit, and this is again behavior associated with self-organized criticality. Also, this power law behavior, maybe I forgot to mention, this is what physicists call scale invariant behavior. So these polynomial decaying quantities are associated with critical behavior of physical systems, and somehow you can observe similar power law behavior in various natural catastrophes, not only forest fires. So somehow this polynomial decay also reflects the fact that when a catastrophe happens so when a lightning strikes a connected component, then the effect of that lightning is going to have a scale-free behavior, and this scale-free behavior is also observed in, for example, earthquakes, another natural catastrophe which is supposed to be governed by self-organized criticality, and also in avalanches. That's why you need a Richter scale to measure the size of the earthquake. So if you remember, if you know, the Richter scale is a log scale. So if there is an earthquake which is Richter 6, then that's, I think, 2 times as much energy is released than in an earthquake with Richter 5. This is a sign that earthquakes have scale-free behavior. So the size or the severity of an earthquake follows a power law behavior. That's why you need the log scale to measure it. And quite similarly, we have power law behavior of catastrophes in the self-organized critical forest fire model as well. Okay, so this is the theorem and this is the phenomenon. So let me say a couple of words about the proof, but this is going to be much shorter than my previous argument because now I'm just going to use the terminology that I developed. So I'm going to show that these limiting quantities that appear in my theorem, I'm going to show that they solve a differential equation. And this differential equation is actually going to look quite similar to the classical Smoluchowski equations for the Erdős-Rényi graph. Namely, for k greater than equal to 2, I'm just going to have exactly the same differential equation as before. So the way components of size k, or the total density of components of size k, if k is greater than equal to 2, evolves exactly the same way as before. Smaller components merge to form a component of size k, and components of size k merge with any other component, and then they cease to be a small. So this is this quantity increases because smaller components merge to form a component of size k, and this term is there because a component of size k merges with anyone else, then somehow that mass goes to component sizes with a different value of k. So for k greater than equal to 2, we have the good old Smoluchowski, but for k equals 1, there is no equation. I'll tell you what happens in k equals 1 later, but there is a boundary condition. So you drop one equation, but you introduce a boundary condition, and this boundary condition just forces your equation to have total mass 1. So I artificially force my quantities to have total mass 1 because I kind of postulate that there is no giant component, there is no mass escaping to infinity, and that implicitly is going to determine k equals 1. But I will describe the heuristic meaning behind this in a second, but let me just mention that the proof of this theorem includes proving that this equation is well posed. That's actually half of the paper. So proving that this is really an infinite system of differential equations which are very intricate. So we actually managed to prove that this system of equation is well posed, meaning that for any reasonable initial condition, there is only one solution to this. There is a solution and there is only one solution to this system of differential equations. By the way, there is no explicit solution. So on the contrary, so if you remember, there was in the Erdős-Rényi case, without the forest fires, there was an explicit formula for Vk of t, but then for this modified equation that we call critical controlled equation, or sometimes we call it forest fire equations. So for this system of equations, we could not find an explicit solution. So we really had to do some analysis to prove nevertheless that this equation is well posed. But then the other thing that you have to prove is that if you look at these quantities that you observe in a finite but large system, so this is the density, or sorry, this is the fraction of vertices contained in connected components of size k at time t, and we want to argue in a system which has total size n, we want to argue that these random quantities or these random functions as a function of time, these converge to a solution of this critical equation as n goes to infinity. And since that has only one solution, we can deduce our theorem. And this second part, so the first part is analysis, and the second part is probability theory, and it again uses these martingale methods. And of course, we use the integral equation instead of the differential equation, but I'm not going to talk more about that. So this is like a panoramic view of the proof, but I still have to explain. So this equation, why the hell do we call it a controlled Smoluchowski equation? So I do not see any control here. And let me explain how we control it. So if you denote by phi n of t to be 1 over n times the total number of vertices of the connected components that burned before time 1 in the random graph. So if a lightning strikes a vertex, then of course the whole connected component burns. And let's say if at time t a connected component of size 100 burns, that means that I'm going to, at that time instant, I'm going to increase this quantity capital phi n t by 100 over n. So this is kind of the total mass of vertices, or the total mass of components that are burnt before time t. And then probably it's not surprising that if you let n go to infinity, then this quantity again going to converge to a deterministic value. So this is the asymptotic total mass of vertices that are burnt by time t. By the way, if a vertex burns twice, that can happen. So if a vertex already burns twice by time t, then I have to count it twice when I calculate this quantity. In any case, this limit exists, and it's part of our proof that we prove that this limit exists. And then if I differentiate it, because now I want to talk about differential equations, then this is this phi n of t. This is going to be the total rate of the vertices, the total rate at which vertices burn at time t. And if you remember, the total rate at which connected components burns. And now again, I'm suppressing the variable t here, but remember, in the forest fire model, if a connected component burns, then that means that it falls into atoms. So there was a connected component, and then we immediately replace it with a number of isolated vertices which have the same mass. So if you look at the time derivative of the total weight of isolated vertices, then of course there is minus v1. That is what happens in the Smoluchowski equation. This is what we had in the Erdős-Rényi graph. So the number of isolated vertices decreases like it did in the original Smoluchowski equation, but then all of the mass which is burned makes the number of isolated vertices grow. So actually infinite components, or sorry, not infinite components, sorry, all of the mass which is burned is kind of infused back into in the form of isolated vertices. So there is this quantity phi, and this is what we call the control function. So there is this phi, and actually, if you look at the other equations, so there is for k greater than equal to 2, we just have our Smoluchowski equations, but then for k equals 1, we have this control function. So what happens is that at criticality, mass constantly tries to escape to infinity due to the coagulations. So if we turn off the fires, then a giant component immediately starts to grow, and if we turn off the fires, then this sum immediately starts to drop below the value 1. But this mass tries to escape to infinity due to coagulations, but we constantly replace the lost weight from an external reservoir in the form of isolated vertices. So we tune this phi in a way that it keeps this sum exactly 1 at all times. So this is why we call it a control function. And then the way we solve it, and I'm not going to say any more about this, so the way we solve it is that we take the Laplace transform, and then we obtain the Burger's equation as before, but now there is an extra term with the control function. So there is this extra term that reflects the fact that we are infusing isolated vertices. And then if you want this condition to hold, then of course in the language of Laplace transforms, you want the Laplace transform at x equals 0 to be equal to 1. That's equivalent to the total weight being equal to 1, and that's equivalent to no giant component. So somehow I want to control my Burger's equation with this term in a way that this boundary condition holds. So this is how we solve it, but I don't want to say more about it other than the fact that we call this the critical controlled Burger's equation. The reason why we put critical there is that this is self-organized criticality that we are talking about. So this is it. This is the end of my talk. This was a glimpse, a very long glimpse actually, a 90-minute long glimpse into my research on forest fire models. But here's the deal. This is time for questions, and a frequently asked questions that I get all the time from combinatorists is, okay, in the Erdős-Rényi graph, when you're at t equals 1, the size of the largest component is n to the 2/3. So what happens in the forest fire model? Because, well, these people studying the Erdős-Rényi graph, they are used to the language of talking about the size of the largest component, and exactly at criticality, this is n to the 2/3. So do you see the same phenomenon in the forest fire model? What is the size of the largest component in the forest fire model? And the answer is more complicated. It's not n to the 2/3, but it's something else. So if you remember, I said previously that we are so happy about the fact that the exact decay of the lightning rate, lambda n, does not have to be fine-tuned, and we see exactly the same theorem, we see exactly the same behavior. So, of course, these VKTs, these are the densities of, like the asymptotic fraction of connected components contained in, the asymptotic number of vertices contained in connected components of size k, when k is 1, k is 2, k is finite. So these are the asymptotical densities of small components, and the exact decay rate of the function lambda n does not affect the behavior in the limit of the densities of small components. However, we will see in a second, at least conjecturally, that the decay of the lightning rate does have an effect on the size of the largest component. So let's see what's happening here. The conjecture is that if you choose the lightning rate to be n to the minus alpha, where alpha has to be between 0 and 1, if we want my lightning rate to be between 1 over n and 1. So if the lightning rate is n to the minus alpha for some fixed value of alpha, then the conjecture is that if you look at some t greater than 1, and if you look at the expected size of the largest component, then it's going to be n to the beta, where beta behaves on alpha in a very funny way. So beta is equal to 2 alpha if alpha is less than 1/3, and beta is equal to 1 plus alpha over 2 if alpha is greater than equal to 1/3. So in particular, if you choose alpha to be exactly equal to 1/3, then you get that beta is equal to 2/3, and that's exactly what you see at the critical graph. And there is an explanation between these two behaviors, but I'm not going to explain it now. What I will explain is that indeed the simulation results, so this is a simulation of a forest fire model with 100,000 vertices, then the conjecture is drawn with green lines. So this is the conjectural graph of beta depending on alpha, and of course this is a log-log plot, and then the true thing that we observe by computer simulation, so the true size of the largest component is plotted with the Ráth function. So well, one might say that based on the simulations, the conjecture seems to be true. And I have to add that I'm working on the solution of this conjecture, especially in this regime where the slope of the green line is 2. So that we are working on the solution of that, working on proving that conjecture in that case. So this was my lecture. If you have questions, please post it in the comment section below. I will answer them, or send an email to me, and I'm happy to answer your questions. Thank you very much.